What's up, everybody? Here are the solutions for worksheet 12, and for this worksheet basically we're exploring Riemann sums, using them to find areas on their curve by taking a limit, some antiderivatives, things like that. So for the first problem I have the function f of x equals 1 over x, and I'm interested in finding the area under the curve for x between 1 and 2. Delta x is going to be 1 over n.
Now, to show you what that looks like diagrammatically, here we have the function 1 over x, just like so. And I'm going between 1 and 2. I'm interested in finding the area over here, right? So we're asked to just kind of draw a rough picture of what that's with 1 over n. For the ith rectangle now, if we're going to use right endpoint, the height using the right endpoint, remember we did this in class, is I just take f of the beginning point of the interval plus I times delta x, whereas for the left, for the height using the left endpoint in the subinterval, well, what I do is I take f of the starting point plus, now I do I minus 1 times delta x. And the area of the rectangle using the right endpoint is going to be this times the height. So it's, if I plug this into f, it's 1 over 1 plus I over n times the width, which is 1 over n. Whereas for the area using the left endpoint is going to be 1 over this expression, so 1 plus I minus 1 times delta x, or times 1 over n. So let's just write it like that. Times 1 over n, which is the width of the rectangle. Okay, now I could simplify these a little bit further. So with this one, if I just distribute the n to the bottom, I just get 1 plus n plus I, right, because this divided by n times that n will cancel. And similarly over here, this is just 1 plus n plus I minus 1, just like so. So now if I sum up the areas for every rectangle, I can get the right approximation using n subintervals. So that's the sum I goes from 1 to n times, not times, of this expression 1 over n plus I, and the left approximation using n subintervals is going to be the sum I goes from 1 to n of the area of the left rectangles. So we have 1 over n plus I minus 1, just like so. And of course, we saw in class, if we take the limit of this as n goes to infinity, we obtain the area under the curve. So the area under the curve is the limit as n goes to infinity of sum I goes from 1 to n, 1 over n plus I, and it's also going to be equal to the limit as n goes to infinity of the left approximation. So sum I going from 1 to n, 1 over n plus I minus 1. And it turns out we will see that this is going to be equal to natural log 2 later in the worksheet. Okay, so just to get more practice with this, I'm giving you a few functions and I'm asking you to find an expression for the area under the curve
And I'll choose to use the right endpoint just because it's a little bit easier. I don't have to worry about that I minus 1, so it looks nicer when I write it. So this is the function. The right approximation is going to be the sum. I goes from 1 to n. Again, it's f of, okay, and the interval is 0 to 9, so it's 0 plus I times 9 over n, because that's going, this 9 over n is going to be my delta x, times the delta x, so times 9 over n. And if I want to get the area, this is just the limit as n goes to infinity of this expression. So let's go ahead and plug it into f. Let's see what that looks like. It's the limit n goes to infinity of the sum I goes from 1 to n of, okay, the function is square root, so I take the square root of I times 9 over n times 9 over n, just like so. Okay, I could pull a 9 out of the square root and multiply it by this 9, etc. I'm not going to do that here, but you can manipulate it a little bit. However, to actually evaluate this limit, that would be incredibly difficult, and we're going to learn methods to do that where we don't have to go through evaluating the limit. For the second function, the same thing, right? So the area is the limit as n goes to infinity of the right approximation, and the right approximation is the sum I goes from 1 to n. Okay, this time my interval is from 1 to 3, so delta x is 2 over n, right? The length divided by n. And I have to plug into f of 1, the starting point of my. Okay, let's
go ahead and do that. So this is the limit as n goes to infinity. Sum I goes from 1 to n. Now my function is this rational expression here, so I have on top 2 times 1 plus 2i over n divided by 1 plus 2i over n quantity squared plus 1 times 2i over n, which is the delta x. Okay, and I'm not going to do anything algebraic with this. It's messy. It's, you know, there's no point, and I doubt there's any way to even evaluate this limit, but that's what the limit will look like. Okay. Lastly, for f of x equals sine of x from 0 to pi, the delta x is going to be pi over n, and so my area is the limit as n goes to infinity of the sum I goes from 1 to n. Okay, it's f of 0 plus I delta x. That's going to be the width. I'm sorry, that's going to be the height. So I have square root sine of I times pi over n, and times just pi over n for the delta x. Another one of those limits that you just can't evaluate, but that's what the area would be under the curve. Now for this problem, what I have is I'm having you guys look at a limit of Riemann sums, and I'm having you try to identify what the function would be. So this right here, for the first one, you should recognize this as being the delta x. This is the starting point of the interval, and this is the I times delta x term over here, right? So my function should be x to the 10th. So basically what I'm doing is this is the same, and I'll write this in definite integral notation, is the integral from starting point 5 plus delta, 5 plus that 2, that's 7, x to the 10th dx. So that's the area under the curve that it represents as a sum. For the second one, this 1 over n, you should realize that that's the delta x, and that's the starting point. So this should be now the integral, lower bound is 1. The width of the interval is whatever's on top of the delta x, so 1. So I go from 1 to 2, that means of ln x dx. For this one, again, I have my delta x here. Starting point is this 2, this negative 2, because I'm subtracting it. So I go from minus 2. The thing that's on top of the delta x is a 4, so minus 2 plus 4 is 2, which means the bounds for my integral are from negative 2 to 2, where they are exactly 4 units apart, and the function is going to be x cubed dx. This one, same story. Delta x is pi over n. Starting point, I'm not adding anything, so it's 0 plus that, so I start at 0, and the width of the interval is pi, so I go from 0 to pi of sine of x dx. And we're going to learn exactly how to evaluate all these on Friday. Now, this one is kind of similar, except now the starting point is negative pi over 2. The width is pi, so negative pi over 2 plus pi is positive pi over 2. And I'm doing cosine of x dx as my function. And one more. This is a little bit hard to see on camera, but what I have is the sum 1 over n e to the power I over n. So the delta x is 1 over n, and that means my starting point, since I'm not adding anything in this exponent, I don't have like 1 plus I over n. I just start at 0. Width is 1, so I go to 0 to 1. E to the x dx. So that's what that's the area that this represents. Now on the last page, we're given an antiderivative. F of x is 2x, and we're asked to find an antiderivative of that, and that's going to be just x squared. I'm going to pick the simplest one since it doesn't specify which one. And remember in one of the tutorials that we had, we were talking about this. I did an example with the velocity and the position function, and we saw that the antiderivative, the net change in the antiderivative should equal to the area under the curve of f. So the net change in this antiderivative that we found up here on the interval 0 to 2 should be, well, it's f of 2 minus f of 0, so that's 2 squared, that's 4, minus 0 is just net change of 4. And the idea is we want to set up the area as a limit. So delta x is 2, starting point is 0, so I'm doing the limit as n goes to infinity of sum I goes from 1 to n, 2 over n, f of x is 2x, so 2 times 0 plus I times 2 over n, right, 0 being the starting point of the interval 0 to 2. And let's do some algebra with this. This is the limit as n goes to infinity, sum I goes from 1 to n. Okay, what do we have? 2 times 2 times another 2, that's 4, 8. I'm dividing by, I have 2 n's in the bottom, so dividing by n squared times I'm sorry, I forgot, this expression is squared. So actually I have 16, my bad. I have 16, because I have 2 2's here. Wait, no, I'm doing the wrong function. It's just, I'm not squaring, it's 2x. So no, it was 8 as before. 8 over n squared times I. Okay, excellent. Now this part right here is a constant, so I can bring it in front of my sum, and so this is now the limit 8 over n squared sum of I as I goes from 1 to n, and I know what this equals. This is the limit 8 over n squared times n plus 1 over 2. And when I take the limit as n goes to infinity of this expression, I look at the lead term here. So I have 8n squared divided by 2n squared. This should be just 8 over 2, which is 4. And notice that it's going to match the result that we got here for the net change in the antiderivative. And we'll see soon exactly why that is the case. So that's the worksheet.